In the last unit, we looked at discontinuities in domain from a graphical perspective. And in this lesson, we're going to take it to the next level with an algebraic approach. So here we go. Recall that there are three different types of discontinuities. The first is called a removable discontinuity, or a hole, and that would be like this one right here on your graph, where it's just missing one little piece, but you could fill it in and make it whole, so that's why it's removable. The next one you have is a vertical asymptote, like we have going on right here between these two pieces, where it either goes up or down. And the last kind is a jump discontinuity, where there's a piece missing, but they don't go all the way up and down to infinity. This is a kind we're not going to be dealing with the algebraic approach, because you basically need a piecewise function or some other funky things that we're not going to be looking at in this lesson. So our third option for algebraic approach is actually going to be none. There are no discontinuities. The function is continuous on its domain. That's the phrase that we're going to use to say there are no breaks, no jumps, no holes, no nothing. And if you remember, the domain refers to all the possible x values of a function, or in other words, it's asking where does this function exist in terms of x values. Where does it exist? So that's what we're going to focus on in this lesson, starting with discontinuities and then moving on to domain. So discontinuities: 1, find, and 2, classify each discontinuity. I've got written in the margins, these are how we're going to do that. So we're going to find discontinuities by setting the entire denominator equal to 0 and solving. And then we're going to classify a discontinuity using the following. If the factor canceled from the numerator and the denominator, then it's a whole, or removable discontinuity. Cancel it out, we remove it. And if the factor stayed in the denominator, then it's a vertical asymptote. And again, we're not going to worry about jump discontinuities at all, talking algebraically. We've only got those two kinds. So let's take a look at our first example, number 1. We have f of x equals x minus 5 over x plus 1. So again, find it, set the entire denominator equal to 0, and solve. So we're going to take x plus 1 equals 0. Solve it for x. We've got x equals negative 1. So that is our first discontinuity at x equals negative 1. And we can't cancel the x plus 1 from the top to the bottom because we don't have an x plus 1 in the numerator. So it stays, and if the factor stays, it's a vertical asymptote. So we have a vertical asymptote. I'm going to abbreviate that VA at x equals negative 1. And that's it. You found it. You're done. Let's take a look at number 2. So again, first find any discontinuities by setting your denominator equal to 0, and we're going to use the zero product property to say each of these we can set equal to 0. So we're going to say, well, what would make x plus 3 equal 0? That gives us x equals negative 3. There's 1. And on the other one, I have root x minus 2 equals 0. How am I going to solve that one for x? Well, if I square both sides, then I get rid of the square root. So I've got squared, 0 squared is just 0. So I've got x minus 2 equals 0, or x equals 2. Now this first one, this comes from the x plus 3, actually does cancel because I have an x plus 3 also in the numerator. So the x plus 3 and the x plus 3 cancels, telling me that this must be a whole at x equals negative 3. On the other hand, this root x minus 2 does not cancel. It stays in the denominator, so this must be a vertical asymptote at x equals 2. Let's actually box our answers. I forgot to do that in the first one. So vertical asymptote at x equals negative 1. And here we've got a whole at x equals negative 3 and a vertical asymptote at x equals 2. Let's keep going. We got number 3. Hopefully, if you haven't written this down already, pause your video and write down the find it, classify it in the margins so that you have it to refer back to. Number 3, again, we want to find any discontinuities by setting the denominator equal to 0. So I take the 4 equals 0 and I go, hang on. 4 will never equal 0. This is never going to work. So that means there's nothing that makes this function discontinuous, and this is going to be one of the cases where we write down our answer as continuous on its domain. In other words, no breaks in the graph. It is what it is. Whole thing, no discontinuities at all. It is continuous on its domain. All right, let's take a look at number 4. Again, find them first. So set the denominator equal to 0, and in order to solve this one, it's going to take a little bit of factoring. So I'm going to factor this denominator, pull out an x, and then turn it into 2 parentheses. I think this gives me an x plus 2 and an x plus 3. And then again, each of these, set them equal to 0. So the first one gives me x equals 0. The second one gives me x equals negative 2, and the third one gives me x equals negative 3. Now, none of these are going to cancel top to bottom, so each and every one of these is a vertical asymptote. So I'm just going to write that vertical asymptote at x equals 0, vertical asymptote at x equals negative 2, and a vertical asymptote at x equals negative 3. And that's all I've got. Vertical asymptotes all the way. Alright, these little thinking men means you're supposed to pause your video now and try these ones out for yourself and then come back and see how you did. So pause your video. Alright, so the first one, factor 2, 2x plus 1 times x minus 7, and the 2x plus 1s cancel top to bottom. So that tells me this gives me a whole at x equals negative a half, and this one gives me a vertical asymptote at x equals 7. And the last one, again, we have something in the denominator with no x's at all, so 3 is never going to equal 0, so we have another one that is continuous on its domain. Alright, if you need a little bit of time, rewind it, rewatch it, go ahead and do that now. Make sure you've taken it all down, because we are moving on. Domain, very similar to discontinuities in the way that we find them, but not quite. And this is where our function exists, all the possible x values we can plug in without having trouble. So, again, we're going to deal with denominators in 0, but this case, to find out where our function is allowed to exist, our denominator can't be 0. In other words, we're going to take the denominator and set it not equal to 0. This is going to let us find the domain. So if x plus 1 is not equal to 0, this, when I solve it, would make it x is not equal to negative 1. The reason that x is not equal to negative 1 is because I have a vertical asymptote there. But when I talk about domain, the allowed values for x, a vertical asymptote is a not allowed value for x. So x is not equal to negative 1. So when I want to write my domain using inequality notation, I'm going to say, well, this is all real numbers, but x is not equal to negative 1, and that would be my answer using inequality notation. Now, if I wanted to use interval notation, it gets a little bit clunky, but I can do it. Don't write this down, as I'm not going to get you to do this. It's not very useful, but this is what it would look like. This would say that we're going all the way from negative infinity up to negative 1, the union from negative 1 to infinity, but in both my intervals, I don't include negative 1, so I jump right over negative 1. Now, this is a bit long, so it's not really worth using, so we're not going to do that. We're just going to think, okay, this is inequality notation. I know it's got a not equals, think unequal, inequality, so I'm not using a less than or greater than sign, but this is my inequality notation. All real numbers, but x is not equal to negative 1. Alright, I got a little thinking man dude thing again, so I want you to pause your video, try this one, and then come back and see how you did. Alright, so again, every place that we have vertical asymptotes, those we're going to exclude from our domain, but we got all real numbers other than that. And this is the same thing we factored up above, so hopefully that wasn't too hard for you to do. Now this last one on this row, again, has a number in the denominator with no variable, so when we were thinking discontinuities, we said continuous on its domain. So now what we're thinking is, okay, so there's no discontinuities, that must mean the entire domain is the set of the real numbers. It's all real numbers. And that would be my solution. Alright, so other than denominators, we have something else that restricts our domain, and that is our radicals. So this says even radicals can't be negative. So this is like even as in 2, 4, 6, 8, not as in even radicals, but this is like a square root, a fourth root, a sixth root. Any even radicals can't be negative underneath the domain or underneath the root sign. So in order to show that, if we want to say something is not negative, that must mean it's greater than or equal to 0. So to find the domain of this, we want to say 7x plus 3 greater than or equal to 0, and then we're going to solve that for x. So move the 3 to the other side and divide by 7. So we've got 7x greater than or equal to negative 3, and then x greater than or equal to negative 3 over 7. That would be my domain right there. Number 11, now we're combining those two things. We've got a root here, and we've got a denominator. So let's take them each one at a time. Let's start with the denominator. We can't have that equal to 0. So root 5 minus x is not allowed to equal to 0. Square both sides to get 5 minus x, not equal to 0. Move the x, and I've got x is not equal to 5. The other thing we have is the root. Doesn't matter that it's in the denominator, it's the thing underneath the root sign, 5 minus x, that has to be greater than or equal to 0. So 5 minus x greater than or equal to 0, move the x to the other side, and I've got x is less than or equal to 5. Now, I have here x is less than or equal to 5, and I also have that it's not allowed to equal 5. So what do I do with that? Well, in order to find my final answer, I need the most restricted domain. In other words, even though this one says that we're allowed to equal 5, saying not equal to 5 is more restricting, gives me fewer options, and so that's actually what I'm going to go with. So as my final answer, I'm going to have x is just less than 5. In other words, this not equals cancels out this equals, and all I have is x less than 5. All right, one more example. I've got h at x is equal to square root of 2x minus 6 over x plus 5x minus 5. So again, let's start with the denominator, not equal to 0. So I have from this one then, x is not equal to negative 5 from the first bracket, and x is not equal to 5 from the second. And then I got to deal with the radical, what's underneath the square root. So just what's underneath, 2x minus 6 has to be greater than or equal to 0. Solve that for x, so I've got 2x greater than or equal to 6. Divide by 2, I've got x greater than or equal to 3. So again, looking for the most restricted domain, greater than or equal to 3, x not equal to negative 5, x not equal to 5. Well, greater than or equal to 3 already rules out that x is a negative 5. Can't have that if I'm greater than or equal to 3. So I can kind of ignore this one because this takes it into account already. And then x is not equal to 5. Well, that 5 is greater than or equal to 3, so I'm going to need both of those things together. So my final answer would be x is greater than or equal to 3, but x is also not equal to 5. And that would be my final answer. All right, 2 more problems for you. Putting it all together. Classify discontinuities and find the domain. We're going to do both. And even though we learned discontinuities first, I'm going to recommend that you do the domain first whenever you see this kind of question. And I'm going to show you in a minute why that is. So let's first tackle the domain. Remember that the denominator is not allowed to equal 0. So that gives me then t is not allowed to equal 0, and root t minus 5 not allowed to equal 0. Each of the factors in my domain, or sorry, in my denominator are not allowed to equal 0. Solve this one gives me t minus 5 not equal to 0, t not equal to 5. And for the root, again, take the thing under the root, that's the t minus 5, and make it greater than or equal to 0. Move it over so t is greater than or equal to 5. Again, we're looking for kind of the most compact way to write this. So t is greater than or equal to 5. We already know t is not going to be 0 because 0 would be less than 5. So I can kind of ignore that. And between the two of these, this not equal to 5 will cancel this equal sign underneath. And that gives me my domain of t greater than 5. That would be my domain, t greater than 5. Once I've got the domain, now I start to think about discontinuities. And the discontinuities, again, come from where our denominator equals 0. So normally we would look at this and we would say, okay, I've got a discontinuity at t equals 0. And I've got a discontinuity at root t minus 5 equals 0, which was going to give me t equals 5. However, both of these things are outside my domain that I already found. So both of these things, I can't have a discontinuity at t equals 0 if my function doesn't even exist at t equals 0. I can't really have a discontinuity at t equals 5 if my function doesn't even exist at t equals 5. So in this case, these discontinuities actually get ignored altogether. And what I've got is that it is continuous on its domain. And the key word here is domain. On its domain, t greater than 5, where the function actually exists, I do not have any discontinuities because the discontinuities that I would have found come from where t would equal 0 and from where t equals 5, and both of those are outside my domain. All right, so again, that's why I wanted to find the domain first so I could know if I even needed to worry about these discontinuities. One more question for you. Pause your video, try this one on your own, then come back and see how you did. Okay, again, so for the domain, I want to make the denominator not equal to 0. So 2 is not equal to root a. So 2 minus root a not equal to 0. So 2 not equal to root a. get rid of the root by squaring both sides. 4 is not equal to a. So a is not equal to 4, 4 is not equal to a, and then the other thing for my domain is I have to have what's underneath the root sign greater than or equal to 0, because it's not negative. So a greater than or equal to 0, nothing to solve there. Now 4 is greater than or equal to 0, so I can't just ignore this part. I do have to take them both into account. So my domain, maybe I should have labeled that t greater than 5 as my domain as well. My domain is a greater than or equal to 0. And a is not equal to 4. And now I'm looking for discontinuities on my domain. So to do that, again, I want to take this denominator and set it equal to 0. So 2 minus root a equals 0 is going to give me a discontinuity, or 2 equals root a is going to give me a discontinuity. And 4 equals a, or a equals 4. Now it did not cancel top to bottom, so if you remember, that means we ended up with a vertical asymptote. So there is a vertical asymptote at a equals 4. So I've got my domain here, and I've got my discontinuity at a equals 4. Alright, that's it. Good luck on the homework and your mastery check.